So here we are in Chapter 2, which is how we see the invisible world. So we're going to be taking a look at different types of microscopy. So here in Figure 2.1, which is at the beginning of the chapter here, we have the bright field microscopy, which is on the left, this photo here. This is what we typically see in a microscope that we would use in a laboratory, or that you may have used in any other classes in a laboratory. And then over here, we see a very different view. In this one, we see our dark field microscopy here, where instead of in the bright field, as the name kind of implies, this area that isn't filled with any organisms is very bright, versus the area here that's not filled with organisms is dark. And so then over here, the organisms themselves are darkly stained or colored, and over here they're very, very bright. So anyway, we're going to move right along here. We'll talk about the properties of light. We'll talk about peering into the invisible world, some of the instruments of microscopy, so a lot of the different types of microscopes, and then we'll talk about staining microscopic specimens. So 2.1 is talking about the properties of light. So this is a little bit of detail into some physics of some light, and this is to help understand how the different microscopes function. So this is kind of the background information to be able to understand the different microscopes completely. So visible light consists of electromagnetic waves that behave like other waves. So you can see this is a wave down here. So the properties of light that are relevant to microscopy can be understood in the term of light's behavior as a wave. So there are packages of photons, packages of light that act as waves. So one important property of the light wave is called wavelength, or as it's defined as the distance between one peak of a wave and the next peak. So you can see in this area down here in part A, we have our wave, which is in green, and then they're showing right here the wavelength. So if you took one peak and went to the next peak, that's the wavelength, or the length of that wave. The height of each peak is called the amplitude. Again, down here you can see amplitude. So if we took this line, kind of made this imaginary line down the very center of the wave as far as height is concerned, and we went from that imaginary middle line up to the very top of the peak there, that is our amplitude. And then in contrast, the frequency of the wave is the rate of vibration of the wave, or the number of wavelengths within a specified time period. So they're showing that here in B. So they're picking this unit of time, let's say from here to here, and then you can see frequency is the number of waves. The number of waves between this part and this part. So if we are talking about a high frequency wave, then you can see down here at the bottom there are many, many waves in that time frame. Talking about medium, there are less waves, and then even less in low frequency. So we have wavelength, which is from one peak to the next peak. We have amplitude, which is from that kind of middle line here up to the top or down to the trough here. And then we have frequency, which is the number of waves in a certain period of time. So interactions of light. Light waves interact with materials by being reflected, absorbed, or transmitted. So reflection occurs when a wave bounces off of a material. So it's reflected. You can think of a mirror, for example. It's reflected back. For example, a red piece of cloth may reflect red light to our eyes while absorbing other colors of light. So the reason we see different colors is because when light is hitting, remember, if you can think back to some of the things you learned about light, with sunlight is actually all of the different colors of the rainbow. And so as this, what looks to be white light is coming in and hitting something, what is reflected back is the color that we see. And what is absorbed, we do not see. So absorbance is when something is capturing that light. So the material captures the energy of the light wave. So what is absorbed are the colors that we do not see, and what bounces back are the colors that we do see. And that's the reflection. So we have reflection, absorption. In the case of glow-in-the-dark they mention here, the energy from light can be absorbed, and then it's later re-emitted as another form, of phosphorescence. So it's absorbing those light waves, but then that particular material is able to then release that or re-emit those light waves. And then we have transmission, which is the third. So transmission occurs when a wave travels through a material, so like light going through glass. And the process of transmission is called transmittance. So there is reflection, absorbance, and transmittance. When a material allows a large proportion of light to be transmitted, it may do so because it's thinner, for example, or more transparent like glass. It has more transparency and less opacity. So if something is very, very transparent, so at high transparency, it has very low opacity. If it's high opacity, then it has low transparency, so something that's not able to be seen through. So we can look down here, and this is where they have an illustration, or not illustration, but two different photos. On the left side here, A, they're showing something that is transparent, like glass, for example. And then B is something that is opaque, not transparent. Light waves can also interact with each other by interference, so they can interfere with each other. Remember, we're talking about light being waves. They're waves moving through the air. And so these waves can hit and bump into each other. And when that happens, it creates a very complex pattern. So dropping two pebbles, this is their example here, like dropping two pebbles into a puddle causes the waves on the puddle surface to interact. So if you drop one pebble into a puddle and then drop another one somewhat close to it, you can see those waves that come off of those pebbles being dropped in the water can actually interact with each other and form really complex patterns in the water. And light waves can do the same thing. So in addition to interfering with each other, light waves can also interact with small objects or openings by bending or scattering, and that's called diffraction. So diffraction is when we have this bending or scattering, when a light wave is coming through and then bounces into some small object or an opening. Diffraction is larger when the object is smaller relative to the wavelength of the light. So remember, the wavelength is the distance between two consecutive peaks of a light wave, or two consecutive peaks of that wave. And then the diffraction, or the amount that it bends or scatters, is larger when the object is smaller compared to that wavelength size. So we've got our wavelength, remember, and it's from here to here. And depending on how small our object is, depends on the diffraction, or the rate of diffraction. So when we talk about all of these different things having to do with light, this is in reference to microscopy and lenses. So refraction is probably the most important behavior that we see in light waves that is related to microscopy and related to lenses. So refraction is when light waves change direction as they enter a new medium. And this is important when we are talking about light waves going through air, and then light waves going through a lens, and then light waves going through the specimen that we are looking at in a microscope. So different transparent materials transmit light at different speeds. Thus, light can change speed when passing from one material to another. So as we're thinking about the microscope, we have our light source at the bottom. In ours, we have a bright field microscope, often used in a laboratory. And we have the light coming through, and as the light waves are going through air, they're at a certain speed. Then it goes through our lens, or let's say through the specimen first. In a bright field microscope, it's going through the specimen, and it's going to change the wave again. It's going to change the speed that's going through it. And then it's going to then hit the lens. So we're talking about refraction, or this change in direction. the change in speed, let's see, back up here, this change in speed usually also causes a change in direction. Refraction, again, a change in direction of light waves, with the degree of change dependent on the angle of the incoming light. So we're concerned with that angle as well, and we'll see some examples here. So here we can see in these illustrations, it's mentioning refraction occurs when light passes from one medium, such as air, to another, such as glass, and then it changes it. So you can see there's light coming in this way here, and then as soon as it gets to this glass, it bends, and it is refracted. And then, as you can see, it goes through the glass here, and then as soon as it gets to air again, it bends again. And then in B here, this is the diagram that shows that same type of thing. So the incident ray, so it's coming in like this, and then we have refraction here. You can see this over here. I don't want to draw right on it, but you can see that it's bending. And then you have reflection, which would be bouncing right back, going this other direction. The extent to which a material slows that transmission of speed relative to empty space is called the refractive index. So we're talking about the air, right? Empty space. So if the light is going through an empty space or going through air and then is changed by something, that difference is the refractive index. So the difference when it goes into glass, for example, or when it is going into water, for another example, or oil. Large differences between the refractive indices of two materials will result in a large amount of refraction when light passes from one material to the other. So for example, light moves much more slowly through water than through air. So light entering water from air can change direction greatly. So there's an example down here, you can see that. And it says that we say that water has a higher refractive index than air. And I think that this picture here is a really good illustration of that. And you can also think of it when you have a glass of water, for example. If you have a glass of water and you have a straw in that glass of water, oftentimes you can see the straw will go in, and then as soon as you get to that water, it looks like it's over here. And that's because of this refractive index, because of refraction. So here you're seeing the same thing. You see this pole is going through, and then it looks like it just goes way off to the side there. It's bending at an angle as it enters the water. And that's due to the large difference between the refractive indices of air, as it's up here, and then water, as it's down here. When light crosses a boundary into a material with a higher refractive index, its direction turns to be closer to perpendicular to the boundary. All right, so when light crosses a boundary, so when we're going from this air into the water here, into a material with a higher refractive index, so water has the higher refractive index compared to air, its direction turns to be closer to perpendicular. So remember, perpendicular looks something like this. If this is our line here, this line here would be perpendicular to the boundary. So more toward a normal to that boundary. So you can see that rather than this pole going this direction still, we're bending to be more similar to this, to a perpendicular. We can think of a lens as an object. So we're talking about lenses here because we're going to be talking about the different microscopes. So we can think of a lens as an object with a curved boundary or a collection of prisms that collects all of the light that strikes it. And then it refracts it so that it all meets at a single point, okay, called the image point or the focus point. So we can scroll down a little bit here. Not quite to the next point, so we'll finish this up here. So a convex lens here can be used to magnify because it can focus at closer range than the human eye. Therefore, it produces a larger image. So we're going to look at an example in a moment here, a diagram, but concave lenses and mirrors can also be used in microscopes to redirect the light path. And we're going to look at a couple different microscopes in this chapter that have multiple lenses and some mirrors to then bend that light to where it needs to be, redirecting it to give it an even sharper image, for example. Figure 2.6, we'll look at in just a moment, shows the focal point, which is the image point when light enters the lens. When light entering the lens is parallel, and the focal length. So, sorry about that, focal length, which is the distance to the focal point. So let's see if we can scroll this up just a little bit, but keep this up here. No, we're going down. So here we are, figure 2.6. So a lens is like a collection of prisms, such as the one shown here. And then here's our convex lens. Our convex lens here is B, and then C is a concave lens. So it says in B, when light passes through this convex lens, it is refracted, bent, toward a focal point on the other side of the lens. And the focal length is the distance to the focal point. So here we have this being bent. All right, so we have our light going in here, and this is our convex lens, and once it gets into here, it's going to start bending, refracting, and then the amount that it's bent, right, is going to be to here. So our light coming in here bends this way based on the curvature of the convex lens. It is refracted toward this focal point. So then we have our focal point there on the other side of the lens. And then our focal length then, as you can see in these dots, is going to be this distance here. So the distance to that focal point is our focal length. Then in C, light passing through a concave lens is refracted away from a focal point in front of the lens. So we have our light coming in this direction, and because this is a concave lens, going this way, concave versus our convex, what we see here is some of the light going out this direction here, and the focal point is actually going to be back here based on the angles. Because this is scattering out this direction, then the point is actually behind here, or in front of the lens, for example. So the human eye contains a lens, a convex lens, that enables us to see images. This lens focuses the light reflecting off of objects in front of the eye onto the surface of the retina, which is like a screen in the back of the eye. So if we're looking at this, for example, as our convex lens, this is a good example right here of what the lens in the eye looks like. And when we have all of this light coming in from whatever it is that we're looking at, our convex lens that are in our eyeballs are going to be collecting this light, and then it bends it, refracts it, and then we have a focal point. And that focal point is actually the back of the eye, back here on the retina, which then goes into the brain through a nerve. So this would be the back of the eyeball. You can kind of course, this is really short here, but then this would be the front of the eye where the light is coming in. All right, so artificial lenses placed in front of the eye, so something like a contact lens, glasses, or microscope lenses, focus the light before it is focused again by the lens of the eye. So it's like putting a lens in front of a lens. So that's pretty clear when we're talking about a microscope lens. You know, the microscope itself has a lens, we can see that, and it's focusing that light into a point, a focal point for us. And then our eye is looking at that focal point that's already been gathered, already been brought to that very clear point, and then it's focusing that onto our retina. But then we also see that same thing happening with contact lenses and glasses, where the convex lens of our eye, for whatever reason, the focal point doesn't match up with the very back of the eye on the retina. And so we have corrective lenses, contact lenses or glasses, that then focus that light in such a way to where our eyeball lens then can then refocus it and make sure that it does land on the retina where it's supposed to be able to make a clear picture that then is sent to the brain. Images are commonly manipulated by controlling the distances between the object, the lens, and the screen, as well as the curvature of the lens. So in a microscopy lab, changing the distance between these things is done often. So changing the distance between the object and the lens. So moving the stage on the microscope up and down is changing where the object is to try to get it into focus. Changing the lens, so switching from a lower powered lens to a higher powered lens is actually a different distance. So changing that distance. And then the screen, we don't change that as much in the microscope because our eyes are where they are, although you can kind of scoot closer in or further away depending on how you want it to be focused. And then as well as the curvature of the lens. So different lenses have different curvatures to give different types of images. Here is their example for a given amount of curvature. When an object is closer to the lens, the focal points are farther from the lens. So it's talking about if you have a lens that is kind of very rounded versus a lens that's not quite so rounded, talking about convex lenses again, then they're going to have very different focal lengths. So then depending on where you need to have your specimen based on that lens. So as a result, it is often necessary to manipulate these distances to create a focused image on the screen. So what we're looking at. So more curvature creates image points that are closer to the lens and a larger image when the image is in focus. This property is often described in terms of focal distance or distance to the focal point, which we've already talked about. All right, so electromagnetic spectrum and color. Visible light is just one form of electromagnetic radiation. So light coming in, the visible light, what we see as different colors, is just one form, and it's a very, very small form. Electromagnetic radiation, or EMR, is a type of energy that is all around us, not just what we see as colors. Other EMR include microwaves, X-rays, and radio waves, including lots of other. So the different types of EMR fall on the electromagnetic spectrum, which is defined in terms of wavelength and frequency. So remember wavelength, so the distance between the two waves, so between this top and this top, versus the distance between these two waves. And then remember frequency is the number of waves in a certain time frame, so from here to here. The spectrum of visible light occupies a relatively small range of frequencies between infrared and ultraviolet light. So let's take a look at that. So here is this electromagnetic spectrum. And you can see we have our wavelength here, frequency, and the amount of energy, which we haven't really talked about. But you can see that this little tiny region right here is the visible light. That's what we can see, is this tiny thing based off of this huge, long scale here. So we don't see cosmic radiation, gamma rays, X-rays, ultraviolet rays, infrared. These are all things that we are unable to see. Just this little tiny section, which then we kind of blow up into this rainbow here, is all the stuff we see. And then these right here, we're talking about the wavelengths. These have different wavelengths. So if we're looking more on the red end of the scale, we have closer to a 700 nanometer wavelength. Over here in the blue end, we're closer to our 400 nanometer. So whereas wavelength represents the distance between adjacent peaks, here we are. Wavelength represents the distance between adjacent peaks of a light wave. Remember, frequency in a simplified definition represents the rate of oscillation. So we're just going over that again. So waves with higher frequencies have shorter wavelengths and therefore have more oscillations per unit time than lower frequency waves. Let's see if we can show that if they show a wave up here. Not so much. So they're talking about the wavelength here. Like we just said, this is 700 nanometers. So closer to this side over here are 700 nanometers with our wavelength over here. And then 400, see they're pretty close on this scale, would be closer to here. I think we're going to see that maybe in another one. All right, back down here. So waves with higher frequencies have shorter wavelengths. Hang on, we're a little off center here. I'm trying to zoom in to make sure you can read this while we're working through it. Wavelengths with higher frequencies have shorter wavelengths and therefore have more oscillations per unit time than lower frequency, right? So that is the definition there of high frequency. So high frequency means more oscillations, more waves, and then shorter wavelengths. So if we have, for example, down here, this is our time, and we have more waves, right? That's higher frequency, which means the wavelength, so the distance between this peak and this peak is short compared to something that's lower frequency, right? Less waves, the distance would be between here and here. So you can see how that's different. If it is a high frequency, it has a shorter wavelength. And if it is a lower frequency, it has a higher wavelength. So higher frequency waves also contain more energy. So if we wanted to add another thing on here, it has more energy. So if you can imagine, if something's going up and down, up and down, up and down, up and down very fast, then it would likely seem like it has more energy than lower frequency wavelengths. They're just kind of going along and going along. This energy is delivered as elementary particles called photons. So these particles are photons. Higher frequency waves deliver more energetic photons than lower frequency waves, right? Because it's going faster, you're getting more photons, it's getting to you quicker. Photons with different energies interact differently with the retina. So remember, the retina is that kind of screen in the back of the eye that's going to collect all these things at that focal point and then transmit them to the brain to be seen, to work out what it is we're looking at. In the spectrum of visible light, each color corresponds to a particular frequency and wavelength. So even in that picture we just saw there, we have different wavelengths and different frequencies here on the scale. And our visible light, even though it's this really small region, has different wavelengths, different frequencies. We see the 700 versus the 400 that we already talked about. All right, so the lowest frequency of visible light appears as the color red, whereas the highest appears as the color violet. So lower frequency of visible light appears as red, and the highest appears as the color violet. When the retina receives visible light of many different frequencies, we perceive this as white light. However, white light can be separated into its component colors using refraction. So if we pass white light through a prism, then different colors will be refracted in different directions, creating a rainbow-like spectrum on the screen behind the prism. So if we have the prism, again, and we have white light, say sunlight, for example, coming through that prism, then we have a rainbow shooting out the other side. You've probably seen a photo of that before. A rainbow color shooting out the other side because those different frequencies, those different wavelengths, are going to go through that prism at different rates. And then that provides the different colors. So the separation of colors is called dispersion. So it's dispersing, right? It's breaking it apart. It's separating into the different colors. And it occurs because, remember, for a given material, the refractive index is different for different frequencies of light. So we're having that white light going through air, and then through air it looks white because it's all coming in together. Our eyes are picking it up all at the same time. And then once it hits that prism, it changes the speed and it refracts differently. That refractive index is different for the different frequencies. And then it separates into the different colors, and we can see that, and that's dispersion. Certain materials can refract non-visible forms of EMR and, in effect, transform them into visible light. So certain fluorescent dyes, for example, absorb ultraviolet or blue light and then use that energy to emit photons of a different color, so giving off light rather than simply vibrating. So we're moving from just the visible light now to different forms of EMR that then can be transformed into visible light. So this occurs because the energy absorption causes the electrons to jump to higher energy states, after which they then fall back down to the ground states, and then that emitting is emitting certain amounts of energy as photons. So if you can remember some chemistry that you have taken, remember we have the center here, and then we've got electrons, well, not really like that, but electrons flying around, and then they jump up to higher energy states, and then they go back down, they fall back down. And then when that happens, they release energy. So the energy absorption causes the electrons to jump up to these higher energy states, but then they can't maintain that. It was just an immediate jump, and then they fall back down, and when they fall back down, they emit that energy as photons. And then we can see that. Not all of the energy is emitted in that given photon, so the emitted photons will be of lower energy. And then, since it's lower energy, lower frequency than the absorbed ones. So, for example, we've got some different dyes. Texas red may be excited by blue light, but then emit red light. You don't need to know these things, these different dyes. The FITC may absorb the invisible high ultraviolet light and then emit green light. In some materials, the photons may be emitted following a delay after absorption. In this case, the process is called phosphorescence, and this is what we see in the glow-in-the-dark plastics. So it's absorbing light, so it's absorbing, let's say, ultraviolet light, something that we don't see, and then it emits other stuff. There's a delay, and it's going to re-emit that. And then we do see that, right? We see the glow-in-the-dark object glowing back at us. All right, so let's talk about magnification, resolution, and contrast. So remember, we're talking about all of these different things, reminding us of chemistry and some physics so that we can then get to what it is that we're seeing and why we're seeing it with a microscope. Microscopes magnify images and use the properties of light to create useful images of small objects, right? Just a little reminder there. Magnification is defined as the ability of a lens to enlarge the image of an object when compared to the real object. So, as you can imagine, right, magnification is the ability of that lens to make something look bigger than it actually is. For example, a magnification of 10x means that the image appears 10 times the size of the object as viewed with the naked eye. So it makes it look 10 times bigger. Greater magnification typically improves our ability to see details of small objects, which I think is pretty obvious compared to, like, if you're watching a video on a small screen, so for example on the phone, if you're watching a YouTube video, for example, on a phone, and then you watch that same YouTube video on a large screen TV, you can see much more detail when you're looking at that larger screen. And that same thing happens when we're talking about a microscope. If we're trying to look at something small, we don't see much detail, but if we magnify it many, many times, we see many more details. But magnification alone is not sufficient to make the most useful images. It is often useful to enhance the resolution of objects. So the resolution of objects is the ability to tell that two separate points or objects are separate. So if we take something and we blow it up really, really big, so I guess, for example, if you took a high resolution or high res video or image, and then you blow it up, let's say it was something that was made on a small screen, and then you blow it up to a big screen TV, for example, we lose that resolution, right? It gets fuzzy. It even says a low resolution image appears fuzzy, and it's hard to tell where the lines are between two different things, whereas a high resolution image appears sharp. And two factors affect resolution. The first is wavelength. So shorter wavelengths are able to resolve smaller objects. So an electron microscope has a much higher resolution than a light microscope because it uses an electron beam with a very short wavelength. So shorter wavelengths are able to have better resolution, as opposed to the long wavelength visible light used by light microscope. The second factor that affects resolution is numerical aperture, which is a measure of a lens ability to gather light. So the higher the numerical aperture, the better the resolution. So the more it can gather light, the more light it can get together, the better you have the ability to distinguish between two separate things, the higher the resolution. So you can imagine the shorter the wavelength and the more light that you can gather, the better of an image you can see, more detail and smaller image. Even when a microscope has a high resolution, it can be difficult to distinguish small structures in many specimens because microorganisms are relatively transparent. So even when we have something that it has a high resolution, something that has a lot of light that it's gathering, something that's using low wavelengths like different EMR, not visible light, like electrons, it is often necessary to increase contrast to detect different structures in a specimen. So the contrast is the differences between the lights and the darks in something, for example, in a specimen. So various types of microscopes use different features of light or electrons to increase contrast. Here's the definition: visible differences between the parts of a specimen. Additionally, dyes that bind to some structures but not others can be used to improve the contrast between images of relatively transparent objects. And that is oftentimes what's used in a laboratory. And we'll see that in a laboratory if we have a laboratory together where we are dyeing different specimens. So there's the gram stain dyes that you perhaps have heard about, gram positive, gram negative. There are endospore dyes, capsule dyes, acid-fast stains. So there are all these different types of stains, and we'll talk about a lot of them in this chapter toward the end here. And all of these different stains are meant to improve the contrast so that you can see certain parts of that microorganism to be able to make identifications, for example. So we're going to move on to 2.2, peering into the invisible world. So we're going to start talking about how people were getting into looking at microorganisms, basically. Some of the fundamental characteristics and functions of microscopes can be understood in the context of history. So we're going to take a look at some of that history. Here, Italian scholar Girolamo Fracastoro is regarded as the first person to formally postulate that disease was spread by tiny invisible seminaria, or seeds of the contagion. In his book here, you don't have to remember all these things here. He proposed that these seeds could attach themselves to certain objects that supported their transfer from person to person. So he was kind of the first person to formally say, this is what's going on, that disease is spread by things we cannot see, these little tiny things that we can't see with the eye, and that they can be on stuff, so on our hands, on clothes, cloth is what's mentioned here, and transfer from person to person. However, since there was no technology for seeing that, it was a hypothesis, it was hypothetical for a little over a century, and then people started to be able to see these things. So we'll talk about some of the early microscopes. We've already talked about it a little bit in the previous chapter, but remember Antony van Leeuwenhoek, sometimes hailed as the father of microbiology. Again, he's credited as the first person to have created microscopes that are powerful enough to view microbes. So he came up with that lens. Born in the city of Delft in the Dutch Republic, he began his career selling fabrics, but then he became interested in making lenses. And because he was able to do that, he did such a good job, he was able to see microorganisms as no one else had done that before. Then he described his observations of these organisms that he saw. People hadn't seen it before, so they initially were pretty skeptical. They didn't think that that was something that was true, since nobody had a microscope or lenses like he had. But then as more and more people were making lenses and checking on it, it became a very popular idea and correct idea. So we have our pictures here. We have A of Antony van Leeuwenhoek, and then we have a very simple microscope replica here. And then C here, we have Galileo Galilei, who we'll talk about momentarily. So while van Leeuwenhoek is credited with the discovery of microorganisms, others before him had contributed to that. So including Italian astronomer Galileo Galilei, who used a compound microscope to examine insect parts. So he also was very interested not only in space and looking at stars, etc. He was also interested in looking very closely at other things. So he actually used a compound microscope, whereas van Leeuwenhoek used a simple microscope. In a compound microscope, we see more than one set of lenses. So down here it mentions Galileo's compound microscope was more sophisticated, and it passed the light through two sets of lenses, versus van Leeuwenhoek's microscope, which is a simple microscope, is going through one lens. So that's the difference between a simple microscope and a compound microscope. Simple is using one lens, and a compound uses more than one lens, in this case two. Van Leeuwenhoek's contemporary, the Englishman Robert Hooke, also made important contribution to microscopy. He published his book, Micrographia, in 1665, and he had made many observations using compound microscopes. So one of them, they talk about him viewing a thin sample of cork through his microscope. And so he discussed and wrote down, he noted that each cavern, bubble, or cell is distinct from the others. So he was the first to really kind of give words to, jot down, make notes of what we talk about as cells, what we now know are cells. It does mention here they likely appeared to Hooke to be filled with air because the cork cells were dead at that point, and so they were just very rigid, kind of empty-looking cells. All right, let's move past that. So again, you should read these. They have important information. They kind of summarize some of the things that we're already talking about, give a little bit more context. All right, so the instruments of microscopy. I think we'll end this portion here, and we can pick up with that in a moment.